So before we discuss that the dispersion curve of diatomic 1D chain, okay, let me first discuss the dispersion relation of 1D monatomic 1D chain. Okay, I have already sent you the link. Okay, let me share this link once again here.
सर मुझे एक डाउट था
एक मिनट okay, let me share the screen. So now I hope my screen is visible to you. Okay, can you see my screen?
yes yes sir.
Okay, so just give me 1 minute. Okay, so just see these vibrations. Okay, okay, can you see this one? This is actually 2D. Okay, before I share 2D, let me share this 1D. Okay, so is a 1D. This is a 1D dispersion relation we have already discussed. Okay, now you can see this the how these atoms are vibrating. Okay, so when I am very close to k tends to 0, so you can see these all atoms are in phase. Okay, the phase means what? These all atoms are moving in same directions. So in acoustic branch, when we are in acoustic branch, okay, and if I reduce the k, you see k, when k tends to 0, then there is no vibrations. Vibration also 0. So we have seen this when we put k is equal to 0, we don't get any acoustic frequency. Okay, so you when k is equal to 0, you have no frequency and they don't vibrate. Okay, as I increase the k value slowly, okay, see, so these atoms start vibrating. Okay, and these atomic chain, they are in phase. Okay, as I keep on increasing the frequency, you see their frequency is increasing. Okay, but what happens when I go near near the boundary regions? Okay, so in this case what happens, instead of moving in phase, okay, they are now moving in opposite directions. Okay, atoms now start moving at the opposite directions. Okay, earlier they were in phase, they are moving slowly, and they were in same, they amplitude in same direction. Okay, if one atom is moving right, other atom is also moving right. If one atom moving left, others also moving left. Okay, but at higher frequency what happens, these start moving opposite directions. Okay, so let us see again what is happening it in low k region. Okay, so when we are in low k region, okay, they are moving in same direction. Okay, so I hope this point is clear to you. Okay, now let me discuss what happens in 2D. Okay, so when we are in 2D, okay, so yesterday we have seen the expression, we get two frequencies. Okay, two frequency, the lower band is, or lower, the split in the frequency graph is split in two part. The lower graph is called acoustic branch, and upper band is called your optical phonon. So okay, optical branch. Okay, so you see the lower one is same what we've seen in monatomic lattice, and the upper one is this upper graph. Okay, now if I reduce the k value, okay, so upper part, when frequency is higher, they are moving in opposite direction. Okay, so that's why they are called optical branch. Okay, the reason will be cleared. I will discuss why this is called optical branch. And the lower one is same what we've done from monatomic. Still they are moving in phase. Okay, so if I go down, okay, if I go down, you see, so the upper and lower branch is in same direction, while they are still the lighter atoms, they are still in opposite directions. Okay, so and if I move to the higher k values, okay, higher k values, okay, so see what happens. So when I move to higher k values, you can see in both the lattices, okay, only both the branches, only one atom is moving. Okay, in the case of this acoustic branch, okay, heavier atoms are only lighter and heavier atoms are moving, lighter atoms rest. Okay, and in the upper branch what happens, your heavier atom capital M1 is rest, only M2 is moving. Okay, So this is the things, these are features of this dispersion curve, which I am going to discuss. And they have given the ratio of M1 M2 also. If the M1 M2 ratio is same, both are same mass, then you don't have any gap here. Okay, you can see the boundaries, both the branch are matching. Okay, as I increase the difference between two masses, so you can see here I have this band gap, the forbidden gap is increasing. Okay, so I hope I have made my points and it will be clear to you. Let us discuss these features now. Okay, so I'm stop sharing now. Okay, so we see and what is happening in 1D lattice. 1D lattice, your atoms are moving at low frequency or low k0, both are moving in phase. Okay, while as you increase the frequency, they start moving opposite direction. And when we are using diatomic chain. Okay, so in the case of diatomic chain, what happens? Now I have this expression. Yesterday we have reached up to this expression. Okay, now let us discuss further what's happening. Okay, so this is my expression. We have reached up yesterday up to this one. Okay, so now you can what you can do, you can write 2 square sine square k by 2, you can write as a 1 minus cos k. Okay, so now this is the expression. So either you can remember this expression, okay, or you can this expression, both are similar. Okay, both are used as the final expressions. Okay, now here, because this is the under root. Okay, so I have to show this is so these values are positive. Okay, this part is less than 1. If this part is greater than 1, then what you'll get imaginary frequencies. Okay, but it does not happen. Okay, so we can show that this portion, okay, is less than 1. Okay, how? So please note down this one. So so then I will show you that this part is positive. Okay, so can I erase this one? Yes, this is yesterday you already written. Huh?
Sir, only third step we have to write.
Only third, yes, only third step. Okay.
Sir, I have one doubt, sir.
Ask.
What is the cutoff wavelength in the graph, sir?
Cutoff, what is the maximum frequency? Maximum frequency. Okay. What we have seen at the corner, the maximum frequency, that is your cutoff frequency. We have plotted this graph now. This was my graph. Okay. This is my cutoff frequency. This at k equal to pi by a and k equal to minus pi by a. What you're getting frequency? This frequency is the cutoff frequency, and corresponding this k, what is lambda? That is cutoff wavelength. Okay, so I told you your lambda can be minimum up to 2a. Okay, so lambda should be equal to or greater than 2a. So your test question I will discuss at the end of the class. Okay, so let me discuss now this thing. So this is my expression for.
Sir.
Yeah.
So in this chapter, the question will be formula based, no?
Formula based. Formula based, approximation based. Okay. The way we will do today some previous questions. I also some questions I have already given to you in your test. Okay, daily practice quiz. Okay, so those kind of questions only they ask. Okay, so now let me discuss. What is this formula means? Okay, so I know 1 minus cos ka. Okay, that is minimum value can be 0. If cos k is 1, so this is 0, or cos k is 0, so this is maximum value can be 1. Okay, so your 1 minus cos a, okay, this lies between 0 to 1. Okay, now let me discuss about this factor. I have to show this factor is less than 1, then will be only positive values. Okay, so now let me discuss this 2m1 m2 1 minus cos ka, okay, upon m1 plus m2 ka square. Okay, now you can see cos ka, okay, minimum value is 0. Okay, so if this is 0, this whole part is 0, isn't it? If this is 0, this whole part is 0. Minimum value, so the minimum value of this whole part is 0. Okay. And if this part is 1, okay, if cos cos k is -1, okay, if cos k is -1, then what will happen? So the maximum value of this expression will be what? 4 m1 m2 m1 plus m2 square, isn't it? So now now this expression at most can be equal to 1. Okay, when m1 is equal to when m1 is equal to m2, then this becomes m square, okay, cancel. So in that condition, 2m square and this 2m square, 4m square, the 4m square can cancel. So this expression also tells that this can be less than 1. So that means this whole what I've written here, that is always less than 1. So these values, what you get here, okay, there is no complex values. Okay, there are no imaginary values. That fact I want to tell. Okay, so I hope this point is clear. Okay, so now let me discuss.
Sir,
So
in this second equation,
Huh.
where we have to put cos k, we have to put 0 in the place of k, no?
see, this value can be either 0, either 1. Okay, so if this whole expression is 0, okay, then this whole expression is 0. Okay, so and if this is maximum value is 2, okay, not 1, so 2, not 2, 1, 2. Okay, if it's pi if it's minus pi, if it is 2, okay, then this become 4 m1 m2 m1 square. Okay, so this value can be should be less than this one, and this itself is less than equal to 1. That means this whole part is less than equal to 1. So this quantity cannot be negative. So this is all, so this minus 1 minus this is always positive. Okay, so you don't get any imaginary things. Okay, is it clear? Okay, so now shall I erase this one?
Yes, sir.
Okay,
We are
Sir?
saying that the
Yes.
imaginary
Sir,
yeah,
cos 1 minus cos k less than or equal to 2 means k value 2, na?
if we cos k is -1, okay, so 1 1 1 minus this can be maximum, this value can be maximum up to 2, na? The cos can be plus minus 1, na?
Sir,
Because cos can be what? If I write, tell me just what you want to ask. Tell me. Let me check once more if it is a mod is there or not. Okay. Let it just 1 minute. 1 minute.
for show that omega can't be imaginary, na?
I just want to show that your this omega cannot be imaginary. Okay, this part will be always positive. Okay, so what I can write here, if I take this positive value mod, okay, this is mod. Okay, if I take this as a mod, okay, then what will happen? This cos k can be and 2 आएगा. Okay, so this I want to show that this part is always positive. Okay, that's not important. Okay, actually that is not given in any book, but I thought just to explain that we are not getting an imaginary part. Okay, so that's why I'm scaling. You can skip this one. Okay, so now we have this expression. Okay, now I want to see, now we have two expression. Okay, so omega plus, okay, omega plus is frequency is called, this branch is called your optical branch, optical phonon branch. Okay, and your omega minus is called your acoustic phonon branch, acoustic phonon branch. Okay, now we have to see how these dispersion curves changes in boundaries. Okay, so we'll see what happens at k is equal to 0, okay, and k is equal to plus minus pi by a, at Brilliant-John boundaries. And what happens when k tends to 0? That is k at k is equal to 0. That near k is equal to 0. And what happens when you go k equal to minus plus pi by a? Okay, at these boundaries, what is the expression for our dispersion? How our dispersion curves changes? Okay, so let us discuss. Okay, so now first put what happens at k is equal to 0. Okay, so when k is equal to 0, okay, my acoustic branch, okay, acoustic branch means lower branch. Okay, so lower branch means I am taking omega minus. Okay, so what happens? This become beta m1 plus m2 m1 m2. Okay, and this become 1 because I'm taking minus lower branch. This will, I'll take minus. Okay, minus under root 1 minus 2 m1 m2 m1 plus m2 square. Okay, 1 minus cos k. Okay, now I'm taking k equals to 0 near k is equal to 0 region. K is equal to 0, so k is equal to 0. What become? This expression become 1. Okay, cos k become 1. Okay, k is equal to 0, cos ka is equal to 1. So my omega minus will become beta m1 plus m2 m1 m2. Okay, 1 minus 1, this become 0, whole become 0, so under root 1 is 1. Okay, 1 is 1, so this becomes 0. So my omega minus is equal to 0. Okay, that means for acoustic, so
Cos k become 1. 1 minus 1, 0. 1 minus 0 will, okay. Sorry, sir.
okay, so this is now your acoustic branch. Okay, we have two branches. Acoustic branch is 0 at k is equal to 0. Okay, so at k is equal to 0, omega minus is equal to 0. Okay, now let me check at k equals to plus minus pi by a. Okay, plus minus pi by a. So when I take k equal to plus minus, okay, so omega k is equal to 0, omega minus 0, I'm writing in this side. Okay, this result you have to remember. Okay, now if I write omega minus, okay, it pi by a, so this become what? Beta m1 plus m2 m1 m2. Okay, so this become 1 minus, this become what? 1 minus, this become cos pi by a. So when, so cos k will be what? Cos ka will be what? Cos pi, and cos pi is what? Minus 1. Okay, so when, so this become what? 2. So this become what? 4 m1 m2 m1 plus m2 ka square. Okay, isn't it? Now solve this one. So if you solve this one, this will become beta m1 plus m2 m1 m2. Okay, now this become 1. Okay, solve this one, so this will become what? If you put here, so this square will come out, so 1 plus m1 m2
beta by m1.
Okay, and this will be in under root. Okay, so this will become what? M1 plus m2 whole square minus 4 m1, so this will become m1 minus m2 whole square. Okay, and if you open this one, this will become m1 minus m2, so this will come this one. Okay, and if you further solve this one, okay, if you further solve this one, minus, this is beta m1 plus m2 m1 m2. Okay, so this will come m1 plus m2, okay, minus m1 plus m2 okay, upon m1 plus m2. Okay, m1 plus m2 cancel. So I'm
Beta
erasing.
upon M.
So I'm erasing this one. Okay. Okay. So this will give me what? Beta. This is square. Okay. Sorry, not a minus. This square. Okay. So this become beta, and this become what? 2m2. Okay.
2m2. 2 beta
2
upon M1 will come.
2m2 or m2 will cancel. So you get 2 beta m1. Okay. So omega minus square you get 2 beta m1. Okay. And if you solve this one, so you get omega minus equal to 2 beta m1. Okay. So I'm writing here at k is equal to plus minus pi by a, I got omega minus equal to 2 beta upon m1. Okay. Now let us draw this curve. Okay. So if I draw this curve, okay, so what we'll get? So we have this curve here. Okay. And this is my k tends to 0. This is k equals to pi by a and k equals to minus pi by a. So k tends to 0. This lower branch, acoustic branch, is 0. This will start from 0. Okay, it will start from 0 and this will go up to what? 2 beta m1, under root 2 beta m1. Similarly, start here, it will go up to under root 2 beta m1. Okay, so this is lower branch. Okay, now we have to calculate now this for next omega plus optical branch. Okay, so I'm erasing this one. Okay, now same we can write for omega plus square. Okay, so what is the expression for omega plus square? Okay, if I write omega plus square, so that will be equal to beta m1 right here, omega plus square. Okay, that will be equal to beta m1 plus m2 m2. Okay, and we have 1 plus under root 1 minus 2 m1 m2 m1 plus m2 ka whole square. You can do it this simple calculation. Okay, and 1 minus cos ka. Okay, now just solve these things. This is for optical branch. Okay, this is for optical branch. Now solve this optical branch at k tends to 0. So when we put k tends to 0, okay, sorry, k not tends to 0, k exactly equals to 0. In that case, what will become? Your omega plus square will become beta m1 plus m2 m1 m2. Okay, and if you solve this one, this will become 1 plus, you put 0 here. Okay, again 1. Okay, so this 1 will come out. Okay, so what you'll get? You'll get omega plus square. Okay, 2 beta m1 plus m2 upon m1 m2. Okay, or you can write omega plus is equal to 2 beta. Okay, that you can write 1 upon m1 plus 1 upon m2. Okay, so this is at k is equal to 0 optical branch. Okay, so let me write this value is at k tends to 0. Okay, so now the next branch. So we have seen if we have a two.
Sir, in this equation, third step, please explain one plus
Which-
1, how you got?
If k is equal to 0, this whole term becomes 0, na? So only you are remaining under root 1,
Okay, sir, now.
or under root 1 is again 1. Okay. Okay. Now, so that means here at the k tends to 0, your optical branch is somewhere here. Okay, your optical branch is somewhere here. Okay, whose value is what? 2 beta 1 upon m1 plus m2. Okay, now check this expression, optical branch at k is equal to plus minus pi by a. Okay, so we have this expression. Okay, so shall I erase this one? Okay, so I am erasing this one. So if I now I have to check this equal to k plus minus pi by a. Okay, so if you solve this for k equal to plus minus pi by a, what will happen now? You have omega plus square beta m1 plus m2 m1 m2. Okay, and this become what? 1 plus, now is become 2 4. Okay, so 4 again, this become m1 minus m2 whole square. Okay, so this will come out m1 minus m2. Last we've done m1 plus m2 same way. Okay, you can do it yourself. Okay, and omega plus square will give me what? Beta m1 plus m2 m1 m2. Okay, and if you solve this one, now what will come? m1 m1 plus m2 somebody's minus m2. Okay, and m1 plus m2 is cancel. Okay, m2 cancel, 2 m1 also cancel, so you will be having omega plus equal to 2 beta upon m2. Okay, 2 beta upon m2 is what? In our case, m2 we have taken as a m2 is our lighter mass. M2 is m for us. Well, remember that thing. Some books they will write opposite. Okay, so for m2 here, for us m2 is a lower mass. Some books will write m1 as a lower mass. Okay, so that depends. Okay, so you should not confuse by seeing these books. Okay, so our case m2 is lighter mass. So now here we have 2 beta 1 upon m1 plus 2 beta m2, that, and at boundaries. Okay, this values goes here. Okay, and it is reach this value. This value is 2 beta upon m2. Okay, and this value is under root 2 beta upon m2. If mass m1 m2 is same, then this gap, there will be no gap. Okay, then there will be continuous frequency. So this that I showed you in the website now, simulations. So this is called your forbidden region. Okay, this is called your forbidden region between these things. Okay, so if mass,
if m2 is our lower mass, now why we are not using their assumption something for a mass?
where
For example, m2 is very much greater. M1 is very
that will see ना, that will see ना. अभी तो हमको पता है कि m2 छोटा है, तो 2 बीटा m2 ज्यादा आएगा, तो ये ऊपर है. 2 बीटा m1 नीचे आएगा, भी m2 कम है ना, तो ये टर्म ज्यादा होगी, इसलिए ऊपर आ रही है. ये जो हैवी है वो नीचे आ रही है, और दोनों में डिफरेंस है, इसलिए गैप भी आ रहा है हमारे पास में. ओके
Sir,
हाँ,
so omega plus is for optical and omega minus is for acoustic, right?
yes. Okay, so now we have seen at boundaries. Okay, so shall I erase this one? Okay, now what happens when you are near to k? Okay, what happens you are near to k, and what happens you are when you are near to boundaries. Okay, so boundaries, you can see the curve is becoming almost constant. Okay, at near boundaries the value is 2 beta m1, this value is 2 beta m2, and here is proportional to k. You know, your acoustic branch is proportional to k. Okay, and your optical branch near k is equal to 0, it is almost constant. Okay, and constant should be equal to this one. Okay, so just now we have calculated on at points. If you want, we can calculate in nearby regions also. Okay, So let us calculate for k tends to 0, k tends to 0 limit. Okay, so not k exactly k equal to k tends to 0 limit. Okay, so if I put okay, so put the heading acoustic branch when k tends to 0. Okay, acoustic branch, okay, when k tends to 0. Yes, and k equals to pi by plus pi by a, it is homework for you. Okay, I'm not going to do everything. Okay, but you should know, remember, it should come constant. So now first we'll do at k tends to 0 what our acoustic branch is there. So we have minus omega square. Okay, and our formula was beta m1 plus m2 upon m1 m2. Okay, and this was okay, this was our 1 for acoustic minus, okay, 1 minus 2 m1 m2, 1 minus cos k, okay, upon m1 plus m2 whole square. Okay, so this was our omega square relation. Okay, now we have to see, so when cos, when k tends to 0, okay, you can write 1 minus cos ka. Okay, you can write cos ka is almost equal to 1 minus x square by 2, so k square a square by 2. Okay, and 1 minus cos ka you can write almost equal to k square a square by 2. Are you getting what I'm saying? When your k tends to 0, not 0, is k is not 0, it's nearby 0. So when you even is 0, then you can open cos x, you can expand cos x by a Taylor series. Okay, for a lower value of k. So this will become your 1 minus k square, this will k square by square 2. So you can write omega minus square equals to beta m1 plus m2 m1 m2. Okay, and you can write here this is a 1 minus, okay, 1 minus 2, okay, k square a square by 2. Okay, and of course m1 m2 is there, m1 m2 2 to cancel, and m1 plus m2 ka whole square also is there. Okay, so now we have what we have, this thing. Okay, now we can put one more approximation here. Okay, now we have this term is under root and k tends to 0, k is 0, this term is less than 1. So whenever we have under root 1 minus x, okay, what I can write,
1 minus x by 2.
1 minus x by 2. Very good. Okay, so I can write this is equal to 1 minus x by 2. So in this expression, okay, I can write omega minus square beta m1 plus m2 m1 m2. Okay, and this what I can write, I can write 1 minus x by 2, that becomes plus x by 2, k square a square, okay, by 2. Okay, m1 m2 and m1 plus m2 ka whole square. Okay, this is cancel, 1 cancel. Okay, now you have m1 plus m2, so omega minus square beta m1 plus m2 m1 m2. Okay, and this become what, this become k square a square m1 m2 upon 2 m1 plus m2 ka whole square. So I can cut this power, this cancelled. Okay, so what I left, so what I left here, I left here beta k square a square by 2 m1 plus m2, and omega minus will be what? If I take minus, so I can write k, okay, this beta a upon 2 m1 plus m2. Okay.
A will also come outside, no?
You want, you can put a, but I want to show this is proportional because this is constant quantity. Okay, a square, this is constant quantity. So omega minus proportional to what? Here we can see this is constant, so omega minus is what? Proportional to k at lower region. That's why I plotted here. For acoustic branch, this is proportional to k. So this is we are getting same thing what we got for monoatomic lattice. Okay, and this, and if we can calculate the if you want to calculate the velocity of sound, we can just differentiate this equation near k tends to 0, d omega by dk. So this will be your velocity of sound. Are you getting what I'm saying? Always when you want to get
ये जो बोला ना डेरिवेटिव वो नहीं समझा, बाकी पहले का समझा।
ये ओमेगा, ये क्या है? ओमेगा इक्वल टू के है. Now you have this near k tends to 0. This is your acoustic branch, and always you calculate your sound velocity from acoustic branch only. So when acoustic branch is k tends to 0, whenever there is linear region, that region, if you differentiate, if you want to calculate now in this region, you want to calculate the phase velocity. Okay, phase velocity, or you want to calculate group velocity, that will d omega by dk, they all will be same, and that will come as a velocity of sound. So omega by k or d omega by dk, all is same, and this will come out what? Your beta a square 2 m1 plus m2. And this question was asked in net, CSIR net. Okay, they have given you the expression, and they asked what is the velocity near what is the velocity of sound, okay, in long wavelength region. So this is the answer. Okay, so this we have discussed. Now what we have discussed? Acoustic branch. Okay, we have discussed acoustic branch where in the limit, when we are at boundaries. Sorry, we have yes, when we are near k tends to 0. Okay, now similarly, let me show what happens to optical branch in k tends to 0 region. We have already calculated at k is equal to 0. Now k near k regions, okay, near k regions, so you can see is coming constant. Okay, it's almost constant here. Okay, so let me show you that one. So now omega plus square. Okay, so omega plus square. So omega plus square is what? What is the expression? Again, write the expression of optical frequency. Omega plus square. Okay, beta m1 plus m2, m1 m2. Okay, and this will come out as a 1 plus under root 1 minus, okay, k tends to 0. Okay, 1 minus m1 m2 k square a square, okay, m1 plus m2. Just now we have solved this for k tends to 0. We have written cos k, 1 minus cos k is equal to k square by 2. So that will be 2 to cancel. Okay, so you were left only, there was minus, now we're taking plus. Okay, the limitation is same,
m1 plus m2 square, sir.
m1 plus m2 square. Okay, the limit is same, k tends to 0. Again I'm using same thing, 1 minus cos k, okay, equal to k square a square by 2. And again you can use that under root limit also. So you have omega plus square. Okay, let me know what answer is coming. Solve. What is the value of constant? Show me what is the value of constant. Okay, so if you write now, I can write beta m1 plus m2, m1 plus m2. Okay, so this become what? 1 plus, again, what should I write? 1 minus x by 2. Okay, m1 m2 k square m1 plus whole square. Okay, now k tends to 0. Okay, so this things, okay, this thing I can take equals to 0. Okay, because we have already k squared is 0 and we are approaching very nearby here. K tends to 0 reason, so there is k square term. Okay, so in comparison to this, now it is plus na. So in this now it's not cancelling. Earlier it was 1 minus, so 1 cancel out. Okay, now it's not cancel, now this is 2. So comparing this to 2, this term is negligible. Okay, so what I'm writing now, omega plus square as 2 beta m1 plus m2 m1 upon m2, and omega plus, you got again 2 beta 1 upon m1 plus 1 upon m2, what we have shown already. Okay, but this value is what? 2 beta 1 upon m1 plus 1 upon m2.
सर उस ब्रैकेट में हमने क्या मतलब जीरो कैसे किया m1 m2
भाई ये के टेंस टू 0 है ना,
वो टर्म तो जीरो है
तो ये टर्म
Okay.
0 के आसपास है. So this whole term is almost negligible compared to 2 na. But this is less, this is almost 0, 0.001, 0.01. Okay, and then the square also there. So if you compare with these two terms, 2, this is negligible, this term. Earlier 1 minus 1, this cancelled out, so we cannot do approximation. Now there is a 1 plus 1, this 2. Okay, so compared to 2, this is negligible. So I have left out this term, so we came here only. So I'm getting again what we have got earlier. Okay, so near the optical branch is almost constant. Okay, that's why we show this type of graph. Here it is almost constant.
Sir, what will be the velocity of sound?
Relative sound you cannot calculate for optical branch. Okay, you only calculate for acoustic branch, that omega k is here. Group velocities you have to calculate, and that it is showing for optical branch it is 0. Okay, so now these are the graph. So I have calculated at k is equal to 0, k is equal to plus minus pi by a, and I have calculated when k tends to 0. Now when k tends to plus minus pi by a, okay, you can check these both branches are going towards constant values. Okay, so that is your homework. Okay, you have to do for k equals to plus minus pi by a. Okay, so you have to do for k equals to, and you can verify your values here. They should come like this. Okay, so for k tends to plus minus pi by a, you have to calculate the this optical values. Okay, so this was, now let us discuss some more properties of this graph. Okay, so let us take a few minutes break now. Okay, I'm taking 5-minute break, and
Sir, group velocity भी 0 होगा इसमें, k tends to 0 में.
वो देखते हैं अभी करते हैं ठीक है. Okay, so let us give me 5-minute break, okay, and then we'll again come back.
Okay, sir.
5 minutes. Okay, just I'm going for drink water and come back. Okay, so you can also take water. Hello. I hope all are present there. No one is left. So now we have seen at boundaries how our dispersion curves changes. Okay. Now why these branches is called acoustic, and acoustic is clear already, like monatomic. Okay. Why this branch is called your optical branch? Okay. So that let me discuss why this branch is called your optical branch. Okay. So what I'm doing here, these formulas you have to remember carefully. Okay, whatever how they are different from your monoatomic lattice. Okay, so I'm erasing this one. I will come. I need this one again, so I'll come back to again. Okay, on this graph. So for the moment, let me discuss why this upper branch is called optical branch. Okay, so when we are solving yesterday, okay, we were having these equations. Okay, you may have equation of 1a 1b. So I will return this equation. Okay, m1 a, okay, minus 2 beta, okay, 2 beta cos k a by 2 b equals to 0, okay, and minus 2 beta cos k a by 2 a, and 2 beta minus omega plus minus square m2 b equals to 0. Yesterday we have seen these equations. Do you remember? Can you check and tell me? Yesterday we written these two equations.
Yes, sir.
Yes, sir.
Okay. So these are the equations. They are omega square. Now because this omega square is plus minus, so I'm writing plus minus. Okay. So now let me calculate now b by, I take this equation and calculate me the amplitude ratio b by a. Okay. So if I calculate b by a, okay, b by a for both positive and both for optical and acoustic. So b by a क्या आएगा? So b by will come your 2 beta minus omega plus 1 square m1 upon 2 beta cos k by 2. Correct? Now let me calculate this b by a. Okay. B by a in the region, what? In the region k tends to 0. Okay. So when k tends to 0, okay, what b by a will become? So limit k tends to 0. Limit k tends to 0. B and a is what? B and a and b are amplitude. Okay, are amplitude of vibration, amplitudes of vibrations. Okay, for heavier and lighter atoms. Okay, A is the amplitude of heavier atom, B is the amplitude of lighter atom. Some book there will be opposite. Don't confuse. Okay, I was shown when we written the equation for heavier atom, I will return this A, M1 I will return A, and M2 I will return this B. So B is lighter atoms. Okay, so some books maybe there will be difference. Okay, now I want to calculate this B by A. Okay, so let us say for minus branch. Okay, so acoustic branch. Okay, acoustic branch. So what we're going 2 beta minus when k tends to 0. Okay, k tends to 0. What is the value of omega minus 1? Okay, just now we calculated 0. It was 0, na? Okay, 0. Okay, so you can use 0, or you can whatever. If you want 0, you can use 0, or you can put whatever value we got from this nearby region k square a square. That also you can write. Okay, so let us put v because 0.
Sir?
Okay,
So can you please explain once? Your voice was not audible by my side.
okay. So now I am now calculating the b by a ratio. Okay, how their amplitude and what is their phase. When I was showing you simulation, I told you in acoustic branch, both are moving in same direction. Okay, when k tends to 0, both are having same phase and same amplitude. Okay, as you increase the frequency, they become opposite phase. Okay, and while optical branch, even in k is equal to 0, both phases were opposite. Okay, so that's I'm going to show here. Okay, so now from this equation I'm calculating b by a. Okay, near k tends to 0, so k tends to 0. Now I'm calculating minus, so you have to write minus here. So k tends to minus 0, so I can write this is 0. Okay, and this 2 beta cos k, what become cos k? This also become 1. Cos k a by 2 become also 1. Okay, so 2 beta cancel. So what become? You get b by equals to 1. Okay, so b by equals to 1. 1 means what? That in acoustic branch, okay, the amplitude, हाँ
1 minus k by 2 क्यों नहीं यूज किया?
कर लो, आप करके देख लो, ठीक है, वो भी करके देख लो. So then you can write here also, you can the same thing you can write here. Okay, so you when your k tends to 0 or k is equal to 0, okay, you will get always b by a equals to 1. Both the atoms will be in same phase. Okay, that means now we have taken 2 atoms. Okay, 2 atoms per lattice point, that we call one lattice point. We say this is a primitive cell. So earlier what we done, that is a 1 atom in 1 primitive cell. Now we have 2 atom in in primitive cell. Okay, so we are getting 2 branches. If we are putting n particle in 1 primitive cell in 1D, so you get n branches. Okay, so now you get b by a is 1. Okay, now let me calculate this for optical branch. Okay, so this is for acoustic branch, same phase. You can write it down. Acoustic, this is acoustic branch. Okay, acoustic branch. So you can write the statement now that this demonstrate that in this case the vibration of 2 atoms have exactly the same amplitude and phase. Okay, so vibration have a same amplitude. Vibration have same amplitude and phase. Okay, for acoustic branch. Okay, now let me calculate this for omega plus. Okay, this for omega plus. Same k tends to 0. Same k tends to 0. Okay, so when you calculate for omega plus, okay, so what we know, when k tends to 0, omega plus is what? 2 beta 1 upon m1 plus 1 upon m1 plus 1 upon m2. Okay, put these values here. So we have 2 beta, okay, minus 2 beta 1 upon m1 plus 1 upon m2 m1. Okay, 2 beta. Okay, cos k again you can write this is equal to 1. Okay, solve this one. What is coming? So 2 beta. Okay, so minus, you calculate, so this is 1 minus, this become what? M1 M2. So M1 plus M2, and this here remaining M1 M1 cancel, you will be having only M2. Okay, so if you solve further, okay, so if you solve further, so this will come as what? 2 beta cancel. Okay, so you will have a M2 minus M1 plus minus M1 minus M2 upon M2. Okay, so M2 cancel, this become minus M1 upon M2. Okay, so the ratio is, now they are not same. Okay, now this demonstrate, okay, that in long wavelength region, Okay, for optical branch, okay, the vibration of two atoms are opposite. Okay, vibration are of opposite phase. Vibration of what? Lighter atom and heavy atom are of opposite phase and have some specific ratio. Now this ratio is not 1, have some specific ratio, some ratio value is some specific ratio, or ratio value is m1 upon m2, have some ratio. Okay, so the phases are opposite and the ratio is m1 by m2. That means B is inversely proportional to m2. Okay, this point is clear. Now why this is called optical branch? Okay, vibration अगर opposite है तो उसको optical branch क्यों बोलेंगे? हाँ बोलो.
So ये last statement what you've told, can you just explain it?
In long wavelength region for optical branch, okay, the vibrations are in opposite phase.
Oh, okay, sir.
Okay, the vibrations are in
सर यहाँ A equals to B से हम एम्पलीट्यूड प्रेडिक्ट करें, लेकिन आप फेज कैसे बोल रहे हैं? मतलब
phase माइनस नहीं है क्या? ये रेशियो माइनस नहीं है इनका. Okay, so now this was your optical branch. Now question is why we call this optical branch. Okay, so in optical branch we have seen these two atoms are vibrating in opposite direction. Okay, now suppose we have a crystal made of ions like NaCl crystal or some KCl crystal. Okay, and then we have these vibrations. Okay, so now these vibrations are going opposite direction. So whenever your vibration go in opposite direction, that time what will happen? They will create dipole moment. Okay, and whenever there is a change in dipole moment, your system, your material, your crystal can absorb and emit light. Okay, have you studied this new atomic physics? Absorption light and emission light takes place what? Change of dipole moment, like in it happens in FTIR. Okay, so IR absorption, it is necessary that there should be change in dipole moment. Okay, for Raman spectroscopy there should be change of polarization. Okay, so now because atoms are moving opposite, so their distance is increasing. That means the two charges they are moving apart. That means there is dipole moment. Okay, so that's why these crystal can absorb up to far IR frequencies. That's why light, that means they can absorb light. That's why they are called optical photon. Okay, I hope I get the answer. Okay, so so now this was your phases at k tends to 0. Now what will happen? This B by A ratio when we take it at billion John boundary. Yes.
Sir, change in dipole moment due to emit for some radiation, na?
So dipole moment, yes, dipole moment changing, na? Because distance is changing, charges are there, they are going apart. So whenever there is change of dipole moment. Okay, if distance is varying, the dipole is what? Dipole is means this plus minus charges, they have some distance. Now this distance changes, d changes. So your dipole moment QD, your dipole moment changes. So this is the change of dipole moment.
And absorb some light, na?
Yeah, absorb light. So,
सर सेम डायरेक्शन पर चेंज होगा तो सर उसमें भी तो डाइपोल मोमेंट क्रिएट होगा.
सेम में तो वो दोनों मूव कर रहे हैं ना, तो उनके बीच गैप कहाँ चेंज हो रहा है? अपोजिट में तो डिस्टेंस चेंज हो रही है ना, उनका जो डी कम ज्यादा हो रहा है ना, डी कम ज्यादा हो रहा है. ओके, so this is your. Now let me discuss again what happens your ratio of this B by A in when you are in boundaries. Okay, so we have 2 beta, okay, minus omega plus minus square. Okay, m1, I am writing again these two equations, minus 2 beta, okay, cos k A by 2 B equals to 0. Okay, minus 2 beta cos k A by 2 A plus 2 beta minus omega square m1 M2 B. Okay. So when we are at the
Sir,
boundaries.
A times will be there, na? A times 2 beta minus first
Yeah, na?
equation. First equation.
A, yes. A. Okay. So just now in the beginning of the class, okay, I have shown you this simulation. Okay. So in the simulation, I told you when we are at the boundary regions. So what happens at boundary regions? What happens at boundary region? Shall I show again?
So please one time.
Yes.
Let me show again. Okay, what happens at boundaries? Okay, so let me share the screen again. I think. Okay. So this is my lattice. Okay, it's moving. So when I am in boundary, so let me first go up to 0, k is equal to 0. So k is equal to 0, you can see these are in same phase and same amplitude. Other that is optical branch, upper crystal, that is moving in opposite direction. Okay, in k is equal to 0. Now I'm going to boundaries. Okay, so let me go to boundaries. What is happening? Can anyone tell me what is happening now?
So both acoustic
opposite
and
direction.
optical both are moving opposite direction.
Both are moving opposite direction. And what other thing you can clearly observe? Can you see in acoustic branch, this lighter atom is in rest, only heavier atoms are moving. Can you check?
Yes, sir.
Okay.
Yes, sir.
And the top branch, what is happening?
Lighter is moving,
Lighter atom
heavier
is
is in
moving.
rest.
And heavier is rest. So that we have to show. That means in for acoustic branch, B by A lighter atom is 0, B by A should be 0. Okay. And for optical branch, A by B should be 0. That we need to show now. Okay. And reasons. Okay. And I also told you if both masses are equal. Okay, if your difference of masses increases, then your gap also increases. Okay, if you difference of masses reduce, then you have similarly no band gap. Okay, both get merges. Okay, so let us stop this one. Okay, and I have to let us calculate now the ratios. Okay, B by A for at boundaries. Calculate and tell me what is happening when you're calculating boundaries. Okay, so when we are at boundaries, let me use first equation again. Okay, to calculate B by A. Okay, so if I use this first equation, I'll get B by A. Okay, for at limit k tends to pi by A. Okay, plus minus pi by A. Okay, plus minus pi by A, and we have 2 beta minus omega minus square m1. Okay, and we have 2 beta cos k by 2. Okay, so let me show now when k tends to pi by a, 2 beta omega square value is what? 2 beta upon m1. Okay, and this is m1, and this is 2 beta cos k pi by 2. Okay, so I can put it if it is near, I can write as a k square by a square by 2. Okay, m1 cancels, becomes 0. That means for acoustic branch, okay, B by A 0, that means lighter atom is at rest. Lighter atom is at rest. Okay, now I have to show for M2. So M2 is not in first equation. Okay, now I have to use this in a second equation. Okay, and calculate second equation again. Shall I erase this one?
Sir, wait a moment, sir.
Lighter atom is at rest. Okay, so can I erase now? No, it's very simple calculation. You can do it yourself. Okay. Now use the second equation. Okay. So again, you write beta B by A. Okay. now plus this one. Okay, so if I want to write b by a, so I can write 2 beta cos ka by 2 upon 2 beta omega plus square m2. Okay, now let me calculate this one. Okay, b by a, or you can calculate a by b also, whatever you want. Okay, so now when k tends to pi by a, okay, this become 2 beta 1 minus k square. What will become this one? What I can write this one? Pi by 2. Okay,
upon 4.
just 1 minute. One. Okay, I have written opposite. उल्टा लिख दिया मैंने.
Yes, sir. Opposite.
उल्टा लिख दिया ना. So this will become now 2 beta. Okay, m2. Okay, m2 omega plus square. Okay, 2 beta cos k by 2. Okay, now if you put p by this one 2 beta minus. Okay,
पहले ही सही लिखा था.
पहले से लिखा था, पहले से लिखा था, पहले से लिखा था, पहले से लिखा था. यहाँ से देखो ना, b by a तो मतलब ये नीचे जाएगा ना, 2 बीटा cos k by 2. Okay, 2 beta minus omega square m2. This is 2 beta cos k by 2. Okay, and write 2 beta. Okay, omega omega plus square is what? 2 beta upon m2, and this is also m2. So m2 cancel, so this becomes 0 niche, so this becomes infinite. Okay, so infinite means what? Infinite means what? Your a is, your b by a is infinite means what? a is 0. Okay, that means a implies a is 0. That means heavier atom is at rest. Heavier atom is at rest. Okay, so you want, if you want, you can do this k tends to 0 and k tends to pi by a expression also, but that becomes slightly longer calculations. Okay, you can do it yourself. Okay, just I have to show that what we have seen, that physics. Okay, by demonstrated physics by this equation. So now we are ready to explain our curve. Okay, now we can see what are the properties of our dispersion curve, diatomic dispersion curve. Okay, so shall I erase this one? Okay, now let me discuss, okay, the properties of our dispersion curve. Okay, so now we have our dispersion curve. Okay, okay, this is minus pi by a, this is plus pi by a. Okay, and this is k tends to 0. Okay, this is acoustic branch, 2 beta upon m1. Okay, 2 beta upon m1, and then we have this optical branch. Okay, this value is 2 beta upon m2. Remember, m2 is lighter mass here. Okay, and this is 2 beta upon m2, and this value is 2 beta upon 1 plus m1 plus m2. Okay, now number 1 point, if m1 equals to m2, okay, m1 equals to m2, okay, number 1, then what will happen? Then forbidden gap becomes 0. Forbidden gap is equals to 0. This gap becomes 0. Okay, this is one thing. What other thing will happen? So when gap becomes 0, okay, so when gap becomes 0, that means you have this type of graph. Okay, so now your frequency range will be what? Okay, now you have a acoustic frequency range. Okay, that will be from 0 to, okay, from 0 to frequency range 0 to 2 beta upon m1, and mass is same, so this your range will be under root 2 beta upon m frequency range. Okay, omega square, this is omega square equal to 2 beta by m. Okay, so this is the frequency range will be acoustic frequency range will be this one. Okay, acoustic frequency range. Okay, and
लिमिट सेम ही कैसे होंगे?
हाँ
दोनों साइड में 0 0 कैसे आएंगे?
क्या 0 0?
लिमिट जो आपने
ये 0 नहीं है, ये सॉरी 0, दिस इज ओमेगा फ्रीक्वेंसी. Omega frequency is 2 beta upon m. Okay, 0 to frequency now varying from 0 to 2 beta m for acoustic branch, and your optical branch starting from here. So optical branch will start from 2 beta upon m to this is what? This will become what? If m1 equal to m2, this become 4 beta m. Okay, under root 4 beta m. If m1 is equal to this become what? 2m, and it's become 4 beta m. Okay, that means what we have seen in our one-dimensional lattice, you're getting same cutoff frequency. Okay, now range is same. So this from this to this is acoustic, and from here to here this is your optical branch. Okay, and there's no gap between. This is first thing. Okay, any question? Now let me discuss second point. If m increases, if heavier mass increases, okay, if m1 increases, okay, so if m1 is increases, so that part will come, this portion will come down. Okay, if m1 increases, this portion will come down and this gap will increase. Okay, if m1 increasing, and so if m1 is increasing, that come, what will happen? Your acoustic branch, okay, drops down. Okay, moves down. Okay, if m1 is increasing, this branch will go down. Okay, it's come down, and if m1 tends to infinite, okay, if m1 tends to infinite, that case what will become? This whole branch becomes 0. This acoustic branch will become 0 here. Okay, and what will happen to this one? If m1 is infinite, so this term is 0, so this again come 2 beta m2. So here boundaries are 2 beta m2. That means this will become flatten. Okay, now you have a single frequency only, this 2 beta m2. I hope what I'm saying is clear to you.
Sir, can you explain once more?
Yes. If m1 is infinite, okay, so m1 is infinite, so this frequency will become what? 0,
Yes, sir.
because m1 is infinite, na?
Yeah.
So this become see, if m1 increasing, it is coming down slowly. Okay,
Yes, sir.
earlier it was here, then it will come here, then it will come here, then it will come. If m is infinite, this becomes 0. Okay, so this is your acoustic, and if m1 is infinite, this term becomes 0. If m1 is infinite, so this term will become 0. So you will have only 2 beta m2. So this is 2 beta m2. This is 2 beta m2. That means what? It becomes a straight line. Okay. So that means your optical phonon. Okay. Optical vibration of single frequency. Okay. Optical phonon. Optical vibration have only single frequency. Have only optical vibration have only single frequency. An acoustic branch frequency. An acoustic branch is 0. And this same approximation was used by Einstein when he given the model of specific heat of solids. Okay, that time he didn't consider this acoustic branch. He only considered this optical branch, and he told that all the atoms in the crystal, when he made assumption to calculate the specific heat, then he told Einstein that all the atoms which are in solid, they all are vibrating with single frequency of in optical range. Okay, and then he calculated the specific heat, but he cannot prove that one. That the final result was wrong. He only able to show the low temperature and low temperature variation. He able to show, sorry, high temperature variation to show. At low temperature, he's not able to show specific heat variation experimentally. He's not able to prove because he has done the wrong assumption. Okay, so he had taken optical range. Okay, then Debye came, and Debye also gave a model of specific heat. That time Debye only considered this model, acoustic branches, and then he told that all the atoms are not vibrating with single frequency. They are from 0 to maximum frequency. Okay, and he told that these all the vibrations, okay, they are omega is proportional to k. They considered only vibrations which are near k tends to 0. Okay, and he was correctly able to show the experimental result. Okay, so that's we are going to when we'll do the thermal properties, specific heat of solids. Okay, so this is the second point. Okay, now what we can yes,
अभी जो आपने बताया मतलब थर्मल वाइब्रेशन जब होते हैं तो वो ऑप्टिकल रेंज में नहीं होते, acoustic की रेंज में होते हैं.
हाँ मतलब वो स्पेसिफिक हीट का जब उसने मॉडल दिया आइंस्टाइन ने, तो उसने ये बोला कि सारे एक ही फ्रीक्वेंसी से वाइब्रेट कर रहे हैं, तो वो वहां पे थोड़ा उसका कैलकुलेशन मिस्टेक हो गया, मतलब उससे वो एक्सपेरिमेंटल रिजल्ट को शो नहीं कर पाया. फिर डेबाई ने वो थ्योरेटिकल मॉडल दिया उसको एक्सप्लेन करने के लिए. उसने बोला कि फ्रीक्वेंसी एक नहीं है, atoms are vibrating with 0 to maximum frequency, and he told that omega the dispersion relation between omega and k, he took linear curve. Okay, because low temperature you have to take linear vibration is very slow, then you have to take linear curve. Okay, and when he took this curve, he was exactly able to explain the t cube variation of specific heat with temperature. Okay, that we will discuss again. Okay, and next
Sir, sir, but in this case, the vibrations are at which temperature, sir?
Huh?
Sir, here we are finding both optical and acoustic.
But
So here
जब टेम्परेचर अगर लो है तो ऑब्वियसली वाइब्रेशन तो आपका टेम्परेचर ज्यादा है तो वाइब्रेशन ज्यादा फास्ट होंगे, हैवियर होंगे. ओके, और टेम्परेचर कम है तो वाइब्रेशन आपके स्लो होंगे, तो उनकी एनर्जी भी होगी. तो वो उसने इसको इससे अप्रोक्सीमेट किया, लो फ्रिक्वेंसी से, लो के वैल्यू से उसने उसको. के क्या है, वेव वेक्टर है, एनर्जी है, तो उसने उसको इससे कंपेयर किया. अगर टेम्परेचर ही नहीं होगा तो सारे वाइब्रेशन तो फ्रीज आउट हो जाएंगे ना. सुपरकंडक्टिविटी में क्या देखा था हमने, if all these vibrations, lattice vibration, they all get freeze out when t is equal to 0. Okay, so now let me discuss the point number 3. Okay, when m1 tends to infinite. Okay, let me discuss what is the third point. Okay, third point is there or not? Okay, yeah, is there. Okay, when m1 decreases. Okay, so when m1 decreases, okay, m1 decreases, or let me show. m2, when m2 decreases. Okay, so when m2 decreases, what will happen? This part will go up, correct? If m2 is small, then this part will go up. If you keep on increasing m2, decreasing m2, this become. And if m2 is 0, then what will happen? Then this branch will be completely, this optical branch will completely disappear. Okay, m2 is 0, optical branch will disappear. Why optical branch will disappear?
infinity हो जाएगा.
Because now if M2 0, that means you have only one atom now. If M2 0, you are monoatomic, and monoatomic case already we have seen we don't have this optical branch. We have only acoustic branch, and acoustic branch that will not get affected. So you'll get only acoustic branch. Okay, so you will get only acoustic branch. Okay, so only acoustic branch will be present. Okay, that is one thing. Okay, now so now suppose point number, this was third, na? Point number fourth. Okay, the point number 4 is if n atoms are present. Okay, if n atoms are present, okay, if n atoms are present in primitive cell or in lattice point, okay, in primitive cell, okay, in 1D, then frequency curve, then frequency curve will split in n parts. Okay, so now when two atoms you have two branches or n parts or branches in 1D. Okay, so if you have three atoms, you will be having three branch, four atom, four branches. Okay, this is 1D. Now we have to see in 2D what happens 2D, what happens 3D. This is only 1D. Okay, now in next class we see when we go for 2D or 3D, how my optical branches changes. Okay, how can I generalize these results? Okay, and we'll solve some previous year problem also. Okay, so let me stop today here. Okay, and tomorrow we'll do generalization of these results. Okay,
Sir,
and we'll see like silicon and the unit cell which have generally two atoms. Okay, how their dispersion curve look like, how dispersion curve changes. Okay, bolo Sivesh.
sir, you are telling that key in primitives in 1D one Brahmins. This last point, can you explain, sir?
So I am telling if you are taking 1D crystal,
Yes, sir.
in the beginning in the 1D crystal I have one atom. Okay, then I brought two atoms in 1D lattice. So I got two
Yes, sir.
branches. If I get three atoms and one lattice point or one primitive cell, then I will have three branches, four branches. That's it. Okay, this is 1D. So 2D and 3D the cases things are different, but we can generalize these results for our real 3D crystals also. Okay.
Okay, sir.
So thank you very much.
And sir, other will be optical और acoustical कैसे समझेंगे सर? जब सर एनाटॉमिक होगा तो ऑप्टिकल एक्वास्टिकल का कोई मतलब नेमिंग ऐसा कुछ होगा?
लॉन्गिट्यूडनल ट्रांसफर्स होगा. ओके, वो कल डिस्कस करेंगे हम लोग. ठीक है, कि कितने लॉन्गिट्यूडनल होंगे, कितने ट्रांसफर्स होंगे, वो 1D में 2D में 3D में वो कल डिस्कस करेंगे. ओके
ओके सर,
Yes.
थैंक यू सर.
थैंक यू.
Thank you, sir.
थैंक यू.
थैंक यू.